All right. Started. Hello, my name's Amy Finley, and I'm with Florida ExpertNet. I'd like to give you everyone a big welcome to our inaugural symposium on expertise systems in Florida universities, collaboration across campus and beyond. I need to apologize a little bit. I had a power outage at my house at the last minute, and so I've relocated to the back porch of my good friends so that I can host this, but you may hear a little bit of construction next door and a bit of wildlife, but hopefully it won't be too bad. Just a little bit of an intro for why we're doing this. You know, the expertise systems, they've been serving universities for businesses and the research community for more than 2 decades. And here in Florida, many of our universities maintain expertise in research information management systems, sometimes several offices within the same institution. And there are several different university producers, managers, and consumers of this information. It includes libraries, offices of faculty advancement, communications, research, industry engagement, and commercialization. And we do have one statewide portal here in Florida, and that is Florida ExpertNet. So I don't know if you are seeing that now on your screen. It doesn't look like it. Yes, you are. There we go. So Florida ExpertNet is a research portal that's been around for a while. We are a granddaddy. That is a portal for promoting expertise across Florida's universities. So it's not, it's across the state. So last year, Florida ExpertNet, we sponsored a national forum on expert finder systems. But in talking to some of our colleagues, we realized, you know, particularly Brian Cooper at FIU, who suggested we really needed a statewide meeting to really talk to each other about what's going on. So we're hoping this will provide an opportunity for all of us to network and explore promising practices, technologies, and data sharing strategies, how to collaborate. It's targeted for Florida's universities that collect and disseminate this information about faculty research, publications, and professional activities, as well as those who would like to be starting to do that. And I want to give a thank you to our steering committee. Let me pull that up. There we go. There's our steering committee for this statewide. You know, there are various, you know, across individuals, across universities. We've come together to plan this. We hope you find it useful. We're certainly looking forward to this. You know, donate a lot of time. Especially like to recognize Carol Ann Dykes-Logue at the Office of Partnership and Innovation at UCF, because she was going to be our host in Orlando. We were disappointed we did not get to meet up there in person, but maybe next year we'll be able to do that. We've got a great program lined up, I think, and we're starting today with Raffaele Vacca. He is, let me get that. There we go. I'm trying to change between these screens. So he's with the Translational Science Institute at UF, and tomorrow we'll have Rebecca Bryant, who's a senior program officer with OCLC. Following the keynotes, we'll be having our lightning rounds where everybody gets, you know, each institution or even just, you know, various groups within institutions get to kind of talk about what they're doing. So we can kind of get a good quick idea of what's going on in the state. We will have time for questions afterwards. So you should see on your Zoom controls, there's a Q&A section. So if you would like to have somebody read your questions, you can type those in there. at any time, but we won't address them till the end of the session. If you'd rather speak your question, if it's, you'd rather say it, then please use the function on your controls that says raise your hand, because then we will allow you to speak. Right now, you don't have controls to speak. That's part of the setup for a webinar. So we'd have to give you that capability, and then you can ask your question at that point. If you have technical difficulties, or we have a couple people who are available, who'll be monitoring the chat to help you out if there's a problem there. So again, you can write your question in the Q&A. You can raise your hand for if you want to speak your question, and then the chat is for Q&A. So I think that we are ready to go to the next person, Chris. So Carmi, can you hand him control, because I'll stop sharing.
Hey everybody, my name is Chris Barnes. I'm with the University of Florida. My primary area is human subjects research and biomedical informatics, but I have had the opportunity for about the last 11 years to work on a large international research networking project called Vivo. And I've been lucky enough to have a fantastic collaborator in Dr. Raffaele Vacca, and I just wanted to introduce him today. He is an assistant professor at the University of Florida in the Department of Sociology and Criminology. But the reason he's here today is because he's also an expert at network analysis and social networking. And so he co-leads our Clinical and Translational Science Institute Network Science Lab. And so he's going to give a fantastic talk today that's going to kind of give you an explanation and a flavor of what we can do when we go to all the hard work of creating these expertise systems. So without these expertise systems and creating the kind of data that shows what kind of networks can be developed and what kind of work people do to collaborate together, it wouldn't be possible to do network analysis. So the work that all of the people that are coming to the symposium do lead to fantastic discoveries. I'm sure I'm not gonna try and steal too much of Raffaele's talk, but I'm hoping he's gonna talk a little bit about, they actually did a research study as part of our clinical and translational science grant from the National Institutes of Health that looked at a network analysis to do prospective matching of joining collaborators together to see if they could induce them to collaborate. And so that was pretty exciting. And they did that based off of network analysis that his team did. So without further ado, here is Dr. Raffaele Vacca. Thank you, Raffaele, for coming and giving us a talk today.
Thank you, Chris. Thank you for this great introduction. And you're correct. Most of the work we were able to do at the University of Florida CTSI was based on data and information extracted from expertise and different expertise systems and databases. And I'm going to talk a bit about that today. Just wanted to make sure that everybody sees my screen here and my cover slide.
Yes, I can see it. Connecting the dots.
Okay.
Computational social science.
Perfect. Okay. Let me just minimize my Zoom window. Yes. So again, Raffaele Vacca here. I come now from about a month and a half of online classes on Zoom, so we kind of know the drill by now. Although it, like I was saying before, it still feels a bit lonely talking to a screen, but I guess we'll have to get used for a while. The title of this talk is about using social network analysis, like Chris mentioned, and computational social science combined with expertise systems and data about scientific collaboration to map and foster collaboration within universities and across different universities. I'm gonna try and cover these topics. First, I'd like to quickly introduce the team that this research is conducted with at the University of Florida, CTSI, and the Bureau of Economic and Business Research, the BEBR. And then I'm going to present a few projects that illustrate at least 3 different types of uses of ways to use social network analysis and computational social science in combination with expertise systems. Network analysis as a tool for description, network analysis as a tool for explanation, and finally, which is what Chris was mentioning a few minutes ago, and it's, I think, one of the most important aspects here, network analysis and computational social science as a tool for intervention. Most of this research is done in collaboration with the University of Florida Network Science Lab at the Bureau of Economic and Business Research and at the CTSI. These are a number of research assistants and postdocs and other faculty. In particular, I'd like to mention Jared Adams, Mark Gerson, Till Krantz, Ray Jamal, Chris McCarty, and Tom Smith, who are the co-authors of most of the papers and research projects I'm going to be talking about today. This lab is mainly supported, like Chris was mentioning, by an optional module, the Network Science optional module at the UF Clinical and Translational Science Institute, which is in turn supported by a Clinical and Translational Science Award from NCATS. And in part, our lab is also supported by the UF BEBR and my own department, my home department, the UF Department of Sociology, as well as a research center that recently joined our efforts here at the University of Florida, the One Health Center for Excellence at the UF Institute of Food and Agricultural Sciences. The CTSI, as many of you know here, the University of Florida CTSI is one of 64 CTSA institutes or hubs in the national consortium of the NCATS. Its mission is to operate as a hub for UF and for the state of Florida for interdisciplinary research in clinical and translational science. The science of translating basic discoveries in the lab, in the clinic, and in the community into interventions that actually improve people's health, individual health, and public health. In 2019, this is an important point that I'll come back to towards the end of this talk. Florida State University joined the UF CTSA hub as a fully integrated partner. And this was very important for us because this meant a shift in the way of thinking about our research and our intervention projects from research and interventions contained within the boundaries of the University of Florida to a more cross-university research and intervention that involved FSU as well as another couple of important partners of our lab, like the University of Kentucky and the University of Miami. The CTSI Network Science module was originally established in 2015, mostly to collect data, to map scientific collaborations at UF, to study incentives and barriers to collaboration, particularly interdisciplinary collaboration in the biomedical sciences and in other sciences as well on campus, and to think about, design, and actually implement interventions to facilitate collaboration both within UF and later across different universities. We currently have 3 aims attached to the optional module of the grant. one, expand network science and the so-called science of science at the University of Florida. Two, map and analyze collaboration networks at the consortium level, so between different hubs and universities within the NCATS consortium. And three, design and implement network interventions both within UF and at the consortium level. And I'm going to talk about research that addresses each of these three aims today. A few words before doing that about the data that were used, that have been used by the lab, and the different data sets that were gathered and developed by the lab. These data include publications which originally were obtained through UF Vivo, and then at some point in time from the Web of Science, and are currently obtained from Dimensions, a database and research information system that I'm gonna say a few words about in a couple of minutes. Our data also include awarded grants. This information was initially obtained from financial transaction data at the UF Office of Research, and then from grants starting in 2016 and later from the University of Florida institutional sponsored research information system called UFirst, and currently also in part from Dimensions. We use data about grant proposals, regardless of whether the grant was ultimately awarded or not. And this information is also obtained from the University of Florida institutional system, UFirst. And finally, some of our research incorporates data about PhD and master committees, student committees at the University of Florida, which are extracted from the information system of the UF graduate school called GIMS, Graduate Information Management System. And we are also using data about spatial locations of faculty offices at the University of Florida, and which is actually pending. We are planning to incorporate in some of our projects data about UF patents, which can be obtained from UF Innovate, as well as in part from Dimensions. Dimensions is a digital science product. It's a database and a research information system that includes information about publications, grants, clinical trials, and patents. It currently includes data about approximately 100 million publications imported from Crossref and other sources like PubMed, 5.3 million awarded grants. This information is ingested from Fed Reporter and similar systems, about 40 million patents, about 550,000 clinical trials, about 400,000 policy documents, and 1.5 million data sets. The way we use Dimensions is mostly through an R package that's called R Dimension, which was developed by our postdoc Till Krantz originally as a team internal tool, and it's now available on GitHub, and we're planning to post it on CRAN, the official public repository for R packages. This is an R package that allows us to search, download, and process data from all the different information sources that are available in Dimensions and through the Dimensions API. So our R package talks with the Dimensions API mostly to import and manage dimension data for use with our network science tools and natural language processing methods. So it does things like constructing collaboration networks from dimension data, combining and convert R vectors into dimensions queries, extract institutional affiliation information like information about home departments from raw address data, or more recently, this is something that is yet to be posted on GitHub. We have an abstract search function that allows us to find all dimensions records, for example, all publications in dimensions that are topically similar to an abstract, an input abstract, or summary text. So the notions, the definitions of scientific collaboration that we are working with here are four mostly. Co-authorship, right? Publication co-authorship, co-author in one or more publications, mostly peer-reviewed articles, co-participating in one or more awarded grants, co-participating in one or more grant proposals, or serving on one or more graduate committees together within a certain time window, typically 1 year. And sometimes we look at these different layers of collaboration together. Other times we look at each of them separately. So in most social networks that I'll be talking about today, the dots that you see here in this slide, the nodes of the network are individual researchers or research communities or teams or entire universities, while the links or edges or ties that you see here, the lines in the visualization here, represent some form of scientific collaboration between those researchers or between those teams or between those universities. So most of these are what network scientists call multiplex networks, networks that may include different types of ties, in this case, different types of collaborative ties, like you see here on the left, the red ties, the red lines represent collaboration on a publication or more publications between scholars. Blue ties represent collaborations on one or multiple grants between scientists. Green ties represent collaborations on both publications and grants between scientists. And most of these are also so-called valued or weighted networks. So social networks whose ties have a weight or value attached to them, representing, for example, the number of publications that were co-authored by two scientists or the number of grants that two scientists are on together. So some measure of frequency or intensity of scientific collaboration between individuals or between organizations. This is just to give you a quick sense of what one of these scientific collaboration networks will look like at a university. This is the social network of collaborations on publications and grants at the University of Florida in 1 year. The dots here, the nodes, are individual faculty or postdocs or graduate students at UF, and they are linked again if they collaborate if they collaborated on a publication or a grant in that given year. Normally in these yearly networks, we have between 5,000 and 7,000 nodes when we look just at one university like the University of Florida. We can use home department information for these researchers to identify departments precisely, or colleges, or more importantly, disciplinary areas. And this is just the main connected component, again, of one yearly collaboration network at the University of Florida, and different colors represent different disciplinary areas. So in blue, you have health-related sciences. In green, food and agricultural sciences, a very important component of what UF research does. In red, engineering, and in black, the College of Liberal Arts and Sciences. And this shows you something that this immediately shows you is that there's a very interesting variation in the degree of interdisciplinarity between teams, right? We easily see clusters of nodes here that are of one color only, right? They are all concentrated into the blue area or the red area, as opposed to boundary teams that gather different colors, right? They gather researchers coming from different disciplinary areas. We are able, using the types of data that I briefly described before, to identify research institutes and centers in these networks. This is an example here. Again, in 1 year, in blue, we have researchers at UF that are affiliated with the UF Clinical and Translational Science Institute, and the blue links represent collaborations between them. So we can, using this data, we can conduct very in-depth analysis of collaborations within an institute like the CTSI, or between the institute and the rest of the university. To the left here, for example, you see in red all collaborations between CTSI researchers at the University of Florida and other UF researchers who are not affiliated with the CTSI. On the right, you see a different visualization now for the UF Cancer Center, a different research center at UF, where in blue you see center scientists, and the red ties are collaborations between them. So within center collaborations within the UF Cancer Center. And in gray, you see what we call the first order neighborhood of these scientists. So the direct collaborators of center scientists who are not themselves directly affiliated with the UF Cancer Center. These are just similar visualizations for other centers like the UF Genetics Institute, and to the right again the UF Cancer Center. So this is just to give you some quick examples and illustrations of what these type of data can show us. They allow us to, for example, identify core research thrusts, core teams within these institutes, brokers or isolates in these institutes, or components of these research institutes that connect them with other distant areas of the university network. The first actual research project using these data and visualizations that I wanted to talk about is one that uses network analysis as a tool for description, and had the aim of identifying research communities at the University of Florida. This was recently published in the paper you see here on the right. The first goal was to identify research communities in these longitudinal collaboration networks that we had for the university. And then we were interested in analyzing patterns of collaboration between these communities. We started from the yearly collaboration network on publications and grants at the University of Florida. And we can use a number of so-called community detection algorithms that are available in network science to identify clusters, or what social scientists call cohesive subgroups, or physicists tend to call them communities in networks. The idea is always the same. A cluster is a group of nodes in a network that collaborate more densely, more closely, well, collaborate in this case, but in general, a group of nodes that interact more densely and closely with each other and more sparsely with the rest of the network. So in a collaboration network like this, a subgroup or community represents a collaborative cluster, right? A group of scientists or faculty who work more densely, more frequently with each other, and more rarely, more sparsely with the rest of the network. These are just 5 examples of collaborative clusters that one of these algorithms identifies in a yearly UF collaboration network. Now, what happens if we have multiple years, if we have longitudinal data? How can we use this information and tools like community detection algorithms to extract stable research communities over the years at a university. Our approach to doing this was to first identify collaborative clusters between UF researchers in each year, and then study patterns of co-membership of authors or researchers in these clusters. So two blue dots here represent two scientists. In this example, those two scientists in the first year, 2013, are co-members of the same collaborative cluster, and then in the following year they are in different clusters, and then in the third year, 2015, they are back again in the same collaborative cluster. So we can draw a line between them. We can infer what we call a co-membership relationship with a value equal to 2 out of 3 years. And this co-membership relationships can be represented again as networks where nodes are individual researchers and ties between them represent their tendency to belong to the same collaborative clusters. And these are again valued ties, right? Some pairs of researchers may currently be in the same collaborative clusters for all the years, for example. Others may be in the same collaborative cluster just for 1 out of 3 years, and so on. And then we can run again community detection algorithms on these co-membership networks to identify our final consistent and stable research communities at a university. There are different possible definitions of co-membership, as you can imagine. For example, intertemporal co-membership in collaborative clusters versus cross-sectional co-membership. So in this paper, we examine different definitions, different possible ways of defining co-membership, the different co-membership networks that derive from these definitions, and how they can be used, the type of research communities that can be identified using these networks. In all cases, the result is meaningful research communities that can be further validated using qualitative methods. For example, we had a research assistant, a couple of research assistants actually going ahead and looking at online profiles of scientists in the same community, and these communities made sense. These were communities of people who were working together consistently over time, or people who had many mutual collaborators, people who were working on the same topics. And for some of these communities, our research assistants actually went to some of these scientists and interviewed them and showed them the sub-networks of these communities that we had identified, and asked them if these were a good reflection, a good representation of their professional environment. An interesting finding was that there were at least 2 distinct types of research communities identified with this method: core communities and bridging communities. Core communities were smaller and concentrated in very specific areas of the university network. Bridging communities were larger, more sparsely connected, and they were bridging precisely very distant areas of the university network. So how can we build on this to then explain things, to explain scientific collaboration, for example, to identify factors that facilitate collaboration, determinants, so-called, of scientific collaboration? We were particularly interested in this project in cross-community collaborations, collaboration between different research communities that we had identified, because these are normally the most novel, innovative, interdisciplinary, and sometimes the most high-risk collaborations. So what are the drivers of these between-community collaborations? One way of attempting to answer this question is zooming out and looking now at the community level networks. So thinking about
communities as nodes and cross-community collaborations as links. And this is what we do here, where nodes in this network are different research communities, and they are linked if their density of collaboration between two different communities is above the median. Different cross-community collaboration networks derive from different definitions of co-membership and therefore from different partitions of scientists into communities. As expected, consistently in all these networks, a large proportion of these communities, between 40 and 50%, do not collaborate with other communities, and that's by definition of a research community, right? Because it's a group of scientists who more closely collaborate with each other rather than with the rest of the network. But for all these networks, we can use statistical models for network data, like exponential random graph models, to explain tie formation, to identify determinants for the existence of a tie in the network. And our findings here was that at the University of Florida, based on these statistical models, cross-community collaborations were significantly more likely when communities were closer in space, when these research communities shared a building, for example, had offices in the same building or in the same floor, when they had similar or shared institutional affiliations, so a higher number of scientists in two different communities belonged to the same department or to the same college, when they had other collaborators in common, so there was a typical transitivity effect that you usually see in social networks. The friends of my friends are my friends. In this case, the collaborators of my collaborators are more likely to also be my own collaborators. And interestingly, we saw an effect for use of UF-CTSI services. Two different communities were more likely to work together while holding all other characteristics equal when their individual scientists tended to use CTSI research services. What about individual collaboration? Collaboration between individual researchers in the same discipline or between different disciplines. The question we had here, this is a different project, is whether individual scientists need to work on the same topics or rather on different topics to collaborate. In other words, whether collaboration between individuals at a university is driven more by similarity or more by complementarity. There is an assumption that a certain degree of topical similarity is needed between people for them to work together. But there is also evidence that some of the most successful collaborations between scientists are synergistic or even interdisciplinary, which means there is a certain degree of topical diversity between those two scientists. So our question was basically how much similarity is too much for a successful and productive and sustained collaboration. We can use topic modeling methods here and natural language processing to measure topic similarity between individual researchers, and then exponential random graphs again to analyze the relationship between topical similarity or overlap and the probability of two researchers working together. The data here are essentially text data, right? Titles, keywords, and abstracts for publications or grants or grant proposals, in addition to the collaboration data that I talked about before. For this particular project, we used data on about 14,000 publications at the University of Florida over 6 years, between 2013 and 2018. We used LSA, Latin Semantic Analysis, to calculate topic similarity between every pair of publications. I'm not going to go into details because I've already been talking for about 30 minutes and I don't want this to be too long, but basically LSA returns what's called cosine similarity, a specific measure of similarity we used to quantify the degree to which two publications have a similar topic profile, the degree to which two publications are close to the same topics or terms and distant from the same topics or terms. The reason why we did this for publications and then averaged it, aggregated it for authors, was because this allowed us to remove the shared abstracts between two authors. When two authors work together, some of their abstracts, some of their publications are exactly the same, and so that would bias upward the topical similarity between two authors. So we remove shared authors and then average the cosine similarity between publications of two authors to obtain a final unbiased measure of topical similarity between two individual scientists. And you see the distribution here between scientists who collaborate and scientists who do not collaborate. And topic similarity between scientists, just like collaboration, can be represented as a network. And that's the network you see on the left here, right? Two researchers are connected here if their level of topic similarity is above a certain threshold. And finally, we use, again, statistical models to determine the association between topical similarity and the probability of collaboration. And we found a quadratic relationship between topic similarity and subsequent probability of collaboration. The collaboration between individuals was most likely for cosine similarity of about 0.1, which was identified as a sweet spot, as a good compromise between similarity and complementarity. This is in a range from 0 to 1. Interestingly, this optimal similarity value is lower than the average similarity of an author's publications to themselves, basically. Of an author to herself. So you want your collaborators to be more different from you than you are from yourself. In a different project, we zoomed out to the university level and looked at inter-university collaboration. I'll be very quick about this. But basically, there's now a growing interest in NCATS and in other funding agencies for studying and promoting collaboration between different universities, or in the case of NCATS, between different CTSA hubs. But we know a lot about collaboration between individuals, but we know very little about determinants and contexts of collaboration between different organizations rather than individuals. We could make different hypotheses. We could think that, for example, CTSA hubs at more prestigious universities are more likely to collaborate with others. We could think that there are homophily effect, what social scientists call homophily effect, the idea that hubs at similar universities, for example, with similar level of funding or similar size, are more likely to collaborate with each other. There could be a geographic proximity effect, and so on. The data we used here are data about publication acknowledgements. Basically, we extracted from PubMed the acknowledgement texts of all publications citing at least one CTSA grant, and when two different CTSA grants are cited by the same acknowledgement, we infer that there is some type of collaboration between those two hubs. So the data here were about 52,000 NCATS funded publications available in PubMed, out of which about 4,000 were cross-hub publications. They were publications whose acknowledgement text cited two different CTSA grants, two different hubs. The result is also, again, a weighted network, now a spatial network, because these hubs have spatial locations, right? They are located at different universities, and it's the network you see on the right here. And then we used exponential random graph models to model the probability of collaboration between two different hubs. We found, for example, that hubs at more prestigious medical programs are more likely in general to collaborate with other hubs, with other universities. There was a productivity effect, so more productive hubs with a higher number of publications and publication per faculty were more likely to establish cross-university collaborations. Interestingly, there was no effect or even a negative effect for funding and private. So funding alone for the CTSI hub did not result in increased cross-university collaboration. And CTSA hubs at private universities were not more likely to collaborate with other hubs. And we did find homophily effects. So hubs at universities with similar levels of prestige were more likely to work with each other, and hubs with similar productivity levels were more likely to work with each other, and hubs with similar size were more likely to work with each other. The final section of this talk is about intervention. How can we use all this knowledge to actually do things, to actually intervene on reality? Network analysis has been studied as a tool for interventions for a long time now, particularly in public health, but really in a number of different fields and disciplines, including marketing, for example, and economics. The idea is to use our knowledge of a social network to promote behavioral change or to even change network structures. And there are different network intervention strategies that have been conceived and studied over the years. This paper here by Tom Valente gives a very good summary. An important difference, which was important for our work, is the difference between induction strategies and alteration strategies. This is a fundamental difference discussed in this science paper and in general in the network intervention literature. Induction strategies for intervention are strategies where we don't really touch the network. We use an existing network to stimulate activity in that network. So there's a network out there, we don't change it, but we try to facilitate or foster interaction in the existing network. The typical example is marketing word-of-mouth campaigns, where we try to stimulate the flow of information in an existing network. This is very different from alteration interventions. In alteration, we actually change the network. We add links or remove links, or add nodes or remove nodes. And these notions can be applied to scientific networks. In fact, traditional research funding, including internal pilot funding, are a form of network induction. What we do is we have a bunch of money and we put it out there and we request applications. So basically we expect the existing scientific collaboration network, we expect the existing network to produce the teams that will apply for those RFAs, right, for those opportunities. And the result is what you see on the left here. These are actual data from a recent UF-CTSI internal pilot program. The result is that people tend to apply with their existing collaborators, with people, with scientists that they already work with. And basically scientists, understandably so, tend to remain in their comfort zone. That would be very different from what you see in the right, from actually creating new links in the network. The idea is that creating new links, so network alteration, may be necessary if our goal is to create more interdisciplinary research or spanning structural holes in the scientific network. There's an increasing recognition that this is needed, right, to address crucial scientific challenges, societal challenges like climate change, translational science, pandemics right now. But this type of interdisciplinary collaborations that form new links, particularly across very distant areas of a university, are rarely produced by the natural evolution of a scientific network. Natural, spontaneous collaborations are more like these to the in the left of this visualization, are more like the red collaborations. Scientists tend to work with peoples in their scientific and professional comfort zone and to replicate past collaborations. There's also more and more evidence that the natural evolution of collaboration networks in science and academia is associated with inequalities like preferential attachment or the so-called Matthews effect in science, a rich get richer and poor get poorer effect in science, or academic caste systems, and so on. So we asked whether alteration strategies can actually be applied to scientific networks. And to answer this, we designed and implemented a UF-CTSI internal pilot program as a form of network alteration, where our intervention units were the research communities that we had previously identified with that method that I described at the beginning of this talk. And the intervention created a new collaborative tie between two scientists in the same community who had not previously worked together. So the intervention increased structural cohesion, what social network analysts call structural cohesion within a research community. In particular, we used network algorithms to identify the missing collaborative link in a community that would maximally increase the cohesion of that community. And then we offered an incentive, professional development funding, to the two scientists at the ends of that missing link for them to attempt a collaboration in the form of submitting a letter of intent to this internal UF-CTSI pilot program. This was designed as a network experiment with treatment research communities and control research communities to then be able to measure a causal effect on scientific productivity of the community. And overall, we recruited 15 optimal pairs of scientists in 15 treatment communities. 8 of those agreed to participate. 5 ended up submitting a letter of intent in exchange for our professional development funding incentive. And out of those 5, so the letters of intent were reviewed, and 3 were asked to submit a full proposal, and those 3 proposals were actually ultimately funded by the UF-CTSI as pilot proposals. And these are the last couple of slides I have, just to mention that what we are doing now is scaling up the same type of intervention, but to a to cross university settings now. So we are now interested in alteration interventions between different universities, particularly between FSU and UF, since, like I said at the beginning, FSU is now a fully integrated consortium partner of the UF-CTSA. And the first step to designing a cross-university collaboration is to find points of convergence between the two universities. So we started by finding common research areas or topics between UF and FSU, based on all UF and FSU publications in 2018 and 19, about 21,000 publications with about 9,000 authors, 7,000 of them from UF and 2,000 of them from FSU. And we ran another topic modeling method, Latin dirichlet allocation, on this body of UF-FSU publications to identify common topics. We identified, thanks to LDA measures, 61 optimal topics that optimally represented topical variation in this body of 21,000 UF-FSU publications. We then retained only the authors who, according to LDA, the UF and FSU authors, had a very high probability of working on those topics. Further, we only retained topics that had a significant proportion of both UF and FSU authors, and this led to 16 intersecting topics or common topics on which both UF and FSU authors worked. And this is just an example. 9 out of those 16 topics, things like physical chemistry, optimization algorithms, weather, sea and climate. So these are more fields or subfields that both UF and FSU authors work on. And this topic overlap, this intersection of topics can be also represented as a network. That's what you see on the right here, where you see UF scientists, FSU scientists, they are connected if they are working on the same topics. And now we are actually implementing this intervention between UF and FSU, where we have selected researcher pairs using these network analysis algorithms and topic modeling algorithms. And we are now at step 3, where we are launching a screening survey to recruit these selected pairs. And the goal is to, again, offer an incentive for them to submit a letter of intent to a UF FSU CTSA pilot program. Final thought, and I'm wrapping up with this, the same type of cross-university intervention can be conducted in a topic-constrained form. So after filtering all publications that are relevant to a certain topic that, for example, the university administration is interested in or the NCATS is interested in. And this was our case with rural health. There was some interest in this specific field. So another version of this intervention restricted publications and topics to the field of rural health between UF and FSU. And I think that's even too long, so I'm gonna stop here, and this will be the time for questions and comments and so on. Thank you.
All right, so again, just real quickly, if you have a question, you can either raise your hand and you'll be asked to speak it, ask the question directly yourself, or you can type it into the Q&A function and get that, and then Chris will read that question. So I'm going to pass it on to you, Chris, if you'd like to.
Sure, Raphael, there's a question from Carol Loeb. She said, this is impressive and informative data. Who uses this information and how do they use it to put practices in place to improve collaborations and build cross-discipline communities? So Raphael touched a little bit on that. Maybe just a little follow-up.
Yeah, well, there's different stakeholders here, right? You can, in our particular case, the main actor who was using this information was the University of Florida CTSI. So any research institute, including federally funded institutes whose mission is to map, study, and especially promote team science, interdisciplinary collaboration, and so on. These would be perfect organizations to use and apply, put this information into practice. But you can easily see university administrations using this type of analysis and data, and obviously funding agencies, right?
So the next question comes from John Katner. He says, why was Dimensions selected as the data source versus other data aggregators, for example, Web of Science?
Well, Dimensions offered a number of services that were particularly helpful for what we were trying to do. First of all, their data are already disambiguated. right? So they basically have author unique IDs for authors and for publications and for other research products. And I imagine that many here in this call know that this is a challenge to do this. So we basically outsource that to Dimensions, even though we obviously validate and test their disambiguation in different ways with our own analysis. And then they had a relatively easy to use API that could easily talk with R and with our packages. Most of our work is based on R, a computer language for statistical analysis. They had a very comprehensive database, including publications, grants, patents, and so on. So there were a number of reasons to select that data source.
Awesome, thank you. So we have.
You have another question.
Yes.
So,
Yes,
Chris,
I apologize. There was a question from Brian Cooper. He's asking, any ability to assess how or to what extent your research of intra or inter-university research teams might impact or reflect successful business industry use of research?
Right, that's a very good question. I think we're not there yet, but this type of analysis could be conducted with patent data to look at basically a business translation, right? What a type of collaborative research within universities and across universities is more likely to lead to patents, for example, or to business applications. So this is a question that can be addressed with some of our data. We have been more interested in health translation so far rather than business translation. But yeah, that's a very good point and question.
great.
I just want to, I'm sorry, go ahead.
Go ahead.
Oh, I just wanted to thank Raffaele for giving us this talk today. I thought it was very interesting, and I hope everyone else thought it was interesting too.
Thank you. Thank you, everybody.
Yes, thank you, Raffaele. That was great. All right. If we don't have any more questions, I guess what we'll do is we'll see you all tomorrow for a talk by Rebecca Bryant. And just a quick note, committee members, if you would stay on for a few minutes, just so we can have a little quick powwow. But thank you, everyone. Thank you, Raffaele. And thank you for all attendees. And we'll be talking to you soon. Thanks.